Hey guys, Mr. Wood back to kind of continue, almost done in chapter 7. But today will be kind of a short lesson. I'm hoping, I don't know, hopefully in less than 15 minutes, 10 or 12 minutes, but kind of continuing what we talked about in class on our Google Meet yesterday. But jokes, I thought I had a good joke yesterday, that Fred and Martha joke. Okay, what goes all around a pasture but never moves? More of a riddle. What goes all around a pasture but never moves? A fence. Okay, what kind of flower grows on your face? Tulips. 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 There you go. Not bad, not great. Okay, where we left off, we were talking about ionization energy. There's three big things you gotta be able to predict about periodic trends. First, you got to know what they are. That's ionization energy, atomic size, which atomic size we're going to get into tomorrow, and electronegativity. So remember the basis behind it is this thing across a row, the Zeph, and I tried to explain that. It's kind of a difficult thing to explain. I probably don't do it very well. But the Zeph, which means the effective nuclear force, is increasing, which means the nucleus is holding tighter to those outer electrons, which means for ionization energy, those electrons over here, these elements over here, are going to have higher ionization energy because of the effective nuclear force. And the reason that's a higher effective nuclear force is because the shielding has decreased. There's not as much shielding from the inner core electrons. And then we send down a column. We said what happens is the outermost electrons are getting further from the nucleus, so they're not held as tight. Thus, they're going to be easier to remove. So the trend then for ionization energy. So again, kind of repeating myself, but just making sure this is definitely something that'll be on our test, will be on the AP test. But if you compare the upper right-hand section of the periodic table to the lower left, we're saying ionization energies have a higher value upper right. Elements upper right have a higher ionization energy than down here. We can now explain why. Because these elements up here have a higher Zeph because there's less shielding, meaning their outer electrons are held with a tighter force by the nucleus, so they're more difficult to remove. Where the elements down here, they are further from the nucleus, so they're going to be easier to remove than elements here. Okay, so again, what we said with ionization energy, we said you got to know what it is. Okay, it's the removal of an electron from an atom. Number two, you got to understand the first, second, third, and fourth ionization energies. Okay, so the first ionization energy is removal of the first electron. The second ionization energy is removal of the second. The third ionization energy is removal of the third. So that's the second thing you got to know. Then you got to be able to explain why. Why do the ionization energies increase from first to second, second to third, third to fourth, or so on? And that is because we still have the same number of protons in the nucleus, but now they have they are pulling on fewer electrons, so they're able to pull those electrons tighter. And then the fourth thing is to predict where does the big jump occur. And the big jump occurs after the valence electrons have been removed. So if we look at an element, say silicon, silicon's got 4 valence electrons. So the big jump is going to occur when we remove the 5th electron or the first non-valence electron or inner core electrons, okay? Okay, so back to the notes. Now there are 2 exceptions, and this will be, it's not a huge thing on our test, but this will be on our test, is to identify where are those exceptions and explain why. So the first exception is beryllium to boron. And here I'm going to jump ahead, and I actually showed you this in class. But if you look at the trend, again, across a row, the ionization energies are increasing with 2 exceptions. So beryllium to boron, which is also magnesium to aluminum. I think this actually occurs for the first 3 rows. So it also would occur calcium to gallium, as well as nitrogen to oxygen, which would be phosphorus to sulfur, and arsenic to selenium. Okay, so we need to be able to explain why is that the case. So, okay, so the So for beryllium to boron, again, the trend is, and you can see the numbers as you go across a row, ionization energies are increasing. We've explained why, because the ZEF is going up, the effective nuclear force is going up because there's less shielding. Well, beryllium to boron is an exception. If you look there, beryllium's value is 899, boron's 800. Well, that's not showing the trend. It's going left to right, it's not increasing. The same thing happens magnesium to aluminum. Again, it dips down. The same thing happens calcium to gallium. Why? And really what I have here, there's really two explanations you could give. One of them, this electron is added to a well-shielded 2p orbital. So that electron that's going, that last electron for boron is going into 2p1, for aluminum is into 3p1, for gallium is 4p1. It's very well shielded by those inner core electrons. So boron by the 1s2, the 2s2. For aluminum, 1s2, 2s2, 2p6, 3s2 is shielding those p1 orbitals. But I think even a better explanation, what it doesn't say here, is that those p1s, the 2p1 for boron, the 3p1 for aluminum, the 4p1 for gallium, is further from the nucleus. Well, it's going to be held together. It's not going to be held by the nucleus quite as strong. And I think that's actually one that I would note. And I think there's, again, it's a multiple choice test, and I think that's what the author of the questions, he or she came up with, is that the reason that this happens is because those p1 orbitals are further from the nucleus, so they are held because of the distance between the nucleus and the outer electron. They're not held as tight, so they're easier to remove. Okay, so one good explanation is that this last electron is added to a well-shielded 2p orbital. But another, maybe even better explanation is that p1 orbital is further from the nucleus. Thus, it's going to be, because it's further from the nucleus, it's going to have a lower ionization energy. Okay, and then the next exception is if you look at nitrogen to oxygen. So if you look at the value, again, the trend is as you go left to right, ionization energies increase. It doesn't happen nitrogen to oxygen. It doesn't happen phosphorus to sulfur. It doesn't happen arsenic to selenium. Why? What's the reason there? Well, it's a different explanation. So just reading what it says here, this electron is being added to a half-filled 2p orbital. So if you think about, remember the 2p's, they fill one at a time. So for oxygen, that 2p4 is now going into an already half-filled orbital. So it must pair up with an electron already in the orbital. And electrons, remember, are negatively charged. And remember, opposites attract, but likes repel. This causes the electron to be more easily removed. It occurs 3 periods down the group. So what I'm saying is, if I were to diagram that, so for oxygen, so the two that I'm talking about, so beryllium to boron. Why does this break the trend? Well, beryllium is 1s2, 2s2. So we've got 4 protons in the nucleus, and then we've got 2, and we've got 2. This is for beryllium. Well, for boron, we've got 1s2, 2s2, 2p1. So it looks 2p1. So it looks like this. We have 5 protons in the nucleus. And then we have 2, 2, and then we have 1 out here. Well, like I said, one explanation that a lot of people give, well, that electron is very well shielded by these. Thus, it's going to be easier to remove because it's shielded. But another, and I think to me almost makes more sense, is that electron is further from the nucleus, so it's going to be easier to remove. Okay, so that's exception number 1, beryllium to boron. Now nitrogen to oxygen, there again, the prediction would be a big jump, but that isn't what occurs. So nitrogen is like this, 1s2, 2s2. This is its electron configuration, 2p3. So if I look at the 2p's, it's like this. So this is the 2p's. So 3 goes single, single, single. So if I draw the little arrow down. Okay, well, oxygen is 1s2, 2s2, 2p4. And again, we're trying to explain, well, why does oxygen not follow the pattern here? Well, again, if I look at the 2p's, it's like this. So we go single, 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 but now it goes in here. Well, this is electrons repel each other, electron repulsion. Light charges repel. And so because of that, that electron and the repulsion from that other electron in that orbital causes it to be easier to remove. Okay, so an ionization energy is definitely is something I would be shocked if it's not on the AP test. It will certainly be on our test as well. Okay, and then finally, ionization energy decreases going down a group, and that's what I talked about, down a group, and that is because we're now filling orbitals of higher energy. So again, if we compare, say lithium, 1s2, 2s1, to sodium, 1s2, 2s2, 2p6, 3s1, that 3s1 is further from the nucleus than lithium, and then potassium would be 4s1. So what I'm saying here is we go down so as we're going down a group, so again in chemistry, so we're talking across a row, but now we're going down a group. So if I compare lithium, which is 1s2, 2s1, compare it to sodium, so again it's like this, so I have 1s2, 2s2, 2p6, 3s1. Well, this is going to be easier to remove than this because it is further from the nucleus. Okay, and then if I have potassium, 1s2, 2s2, 2p6, I'm struggling, 3s2, 3p6, 4s1. Well, again, this is going to be easier to remove, this outer electron. Its ionization energy, the removal electron, is going to be easier to remove because it is further from the nucleus. Okay, so what ionization energy is, the first, second, third, fourth ionization energies. Why do those increase? Where's the big jump? And then what is the overall trend, and be able to explain the trend. Okay, almost done. I told you it wasn't going to be too long today, but I do want to just talk briefly about this next thing, which is not as big. There's one more bigger thing to go, and that is going to be atomic size. And you got to, as well, you got to remember the exceptions. So ionization energy, what it is, what it means, first, second, third, fourth, so on. Why do those increase? Where's the big jump? What's the trend? And explain the trend and remember the exceptions. Okay. Electron affinity. So I'm just going to go over this. This is not a huge thing. This is not on our test. And, I can't imagine it be on the AP test. It's kind of the opposite of electron affinity is kind of the opposite of ionization energy. And I think of this kind of with electronegativity. The energy change associated with adding an electron. It's a different definition, but the same trend. And the electron affinity increases going left to right. And if you notice these values are negative, which means it's exothermic. And when the addition of when something becomes more stable, energy is given off. When bonds form, we'll talk about next semester. We'll probably talk about in January. But it'll be negative, and the bigger negative it is, the more stable it is. And so that's what this is saying. So the energy change associated with adding an electron to an atom, and it's exactly the same trend as ionization energy. So I'm not going to hold you to the exceptions for this. So I'm going to stop there, and guys, we will finish the chapter on Thursday. We'll have to have a pretty effective day on Thursday, and I am done. See you guys on Thursday. Bye.